Hi everyone, welcome to the Developing Artificial Intelligence Using Machine Learning at the Edge with Embedded Micro SoC FPGAs class. My name is Grant Jennings. I'm the Director of International Marketing for Gowin Semiconductor, and we're going to talk a little bit about how to deploy machine learning models at the edge using FPGAs with microcontroller capabilities. So the agenda is first, I'm just going to give an introduction to machine learning at the edge and the differences between machine learning at the edge and cloud-based machine learning. You probably are kind of already aware of this if you're taking the class, but I just want to recap the differences of what we'll be doing compared to more common platforms that may be available. So I'm going to also cover TensorFlow, TensorFlow Lite, and TensorFlow Lite for microcontrollers. So for this platform, we're going to use TensorFlow, and within TensorFlow, there's basically quantized and optimized capabilities for application processors as well as microcontrollers and embedded hardware. So we'll talk a little bit about that. Then we'll go into the system architecture that we'll be using for this hardware platform and some of the differences between the low end and more the higher end and what we have available. Then we'll go into the design flow. So we're actually going to go through training a model, generating what's called a flat buffers file. Flat buffers or TF-Lite file. So this is basically a quantized and optimized file for embedded hardware. And then we'll go through generating the firmware and deploying it on the development boards. After that, we'll talk about some of the hardware platforms that we have available. The GW1 and SR4, which is a 4K lookup table FPGA with hardened Cortex M3. Then we'll talk about the GW2 AR18 board, which both of these boards, the 1 and SR4 and the AR18, have extended memory. And then we'll talk about the GW2A55 board, which is even larger FPGA, gives you a little bit more room to prototype and develop with. After that, we'll go into actually training a model for a person classification example. We'll go through training a model for audio phrase detection. And then lastly, we'll go through some of the cases that you may want to use an FPGA for versus a microcontroller or application processor, and some of the unique flexibilities that you have with the micro SoC or standard FPGA platforms over, say, a microcontroller or application processor. And I'll give just some links to support and resources that you may need to continue on after this class. First, I want to just go through the prerequisite software that you'll need to go through the class. And like I said, since this is a digital conference and since we were unable to obtain the attendees list prior to the event, you can install the software and get it ready. You will be required, particularly for Gowin EDA, to attain a license. The license is free, but it will take, there's about a 24-hour turnaround time on that license, unfortunately. So that's going to kind of block you from being able to go through the entire flow. But if you install it now, you can go through this while we go through the rest of the course, and you can be downloading and installing it in parallel. So first is Gowin EDA, which is at gowinsemi.com. It's absolutely free, and it gives you full access to the FPGA synthesis suite, access to all FPGA design IPs for free, and access to other tools within the software, such as Gowin's internal logic analyzer. So you have an internal logic analyzer that you can use within the FPGA. And this is, I'd recommend continuing to update Gowin EDA as new releases come out about every few months or so, because there's always new IPs and new software features being added. So I know when I download the next version, I'm always impressed at what has been added. So it's worth keeping up with. Um, to get the software, just sign up for a Gowin semi.com account and then request the license with your MAC address, and you should receive it within 24 hours. Next tool you need is Kyle, and you can get this at kyle.com. It's the free version's okay. There is a paid version. It just allows you to do larger C code for a Cortex M processor. So you can use the free license except for audio phrase detection demo, because there's some additional C code needed for that demo to do some of the processing of the spectrogram data. So that's the only one that the code is longer than what's allowed on the free license. But fortunately, there is a free trial version that you can use for, I think there's like a 7-day and a 30-day license. So that allows you to at least try it out. But for everything else, the free version's okay. And then Python 3, you'll need to run some of the executables and scripts. So first, let's just introduce machine learning at the edge and what at the edge means. So most platforms, as machine learning has become popular and used in hardware, typically it connects to the web to do the machine learning portion of the effort. So for example, let's say that you have a doorbell camera and it has some machine learning capabilities where it can recognize, uh, mail or a post mail officer versus a standard person. Well, it's likely going to go to the cloud to do that processing, where there's a healthy amount of resources to enable that machine learning capability. However, that connection to the web is a challenge in many applications. For example, let's say that you want to monitor something very remote on, a battery over time, and you really don't want any connectivity, or you do want connectivity, but really you want to do the processing locally. You want to determine what object is being seen in, let's say, an image, and then after that, you just want to send maybe a digital message, very low bandwidth message over the web to uh, tell a system to do some sort of effort. That's the difference between uh, edge computing and machine learning at the edge versus more traditional machine learning, is that all of the inference, all of the intelligence is pushed to the embedded hardware that sits at the edge locally versus doing the processing over the web. And so that poses a lot of challenges. You're typically using hardware that is not as powerful than, say, a server or a really high-end performance machine. And so there's trade-offs that need to be made. So let's just go through this list really quick. Cloud computing, dependent on the internet server or cloud connectivity to do the processing. You can train and retrain models on the same platform. So that's a fundamental difference. Most of the edge computing platforms do not involve training. They have already trained a model on a server in the cloud, and then after the model is trained, they use just the trained model on the embedded hardware. That uses a lot less resources than the training. Training is, even on a really high-end machine, can take several days, even with GPUs to train. So that's still pushed to typically the cloud, and then on the edge, typically you don't have to train or retrain, and if you do, then you may go to the cloud with some new information and retrain later. Uh, Cloud computing is certainly higher performance, but it is also much higher power. So, these machines are typically not something that you can have locally, or it'd be very expensive to have locally. Okay, and then on the edge computing side, no connectivity is required to do the machine learning activity. So that's very nice. Retraining is typically still done uh, uh, through a server in the cloud, and typically edge computing is lower performance, but is also much lower power. So it can be even powered by a battery, which can be really nice for remote applications. Okay, TensorFlow for edge applications. So many of you probably know the machine learning platform TensorFlow, and TensorFlow is one of several different machine learning platforms that allows you to develop models, and train models and deploy and run models on your computer or or a server, um, depending on what you'd like to do. However, there's actually some sub tools within TensorFlow focused on targeting embedded hardware. So the first one is TensorFlow Lite, and this is machine learning for edge applications, but it's really focused on running models, train models on mobile devices such as smartphones and tablets, and on kind of like A-series processors. And then the second one is TensorFlow Lite for microcontrollers, and sometimes it's abbreviated TFLU. And this is for machine learning on, as it says, microprocessors. So what these two sub-tools do is they optimize the model and quantize it for embedded hardware. And so basically models that originally, the big thing is originally used floating point in TensorFlow are reduced down to 32-bit or even 8-bit integers, 16, 32, or 8-bit integers. And there's really not a whole lot of reduction in performance of the model. There is a little bit, but research has shown that it's fairly minimal. And so on our platform, we actually leverage this because it provides a open source path to do this optimization and quantization. So yeah, a model is optimized and quantized to improve performance and reduce computational resources for embedded devices. And so in our case, we typically focus on 8-bit integers because it's a really nice balance between performance, any performance loss, and compute needs. So floating point values in TensorFlow are converted to 8-bit integers. And then there's some additional steps. So a flat buffers file is generated, and this flat buffers file is what TensorFlow Lite for microcontrollers generates. And basically this contains the model as well as the coefficients. It's kind of like an instruction file, so to speak. And so this is generated from the train model PB file, and we take that and we basically parse it, and we parse some things into running on the microcontroller, and then we parse other things to the Go AI NPU. And so yeah, flat buffers file just provides instructions defining the model, and then as well as the quantized weights and bias coefficients that are needed for the train model. So now I'm going to talk a little bit about system architectures for using TensorFlow Lite for microcontrollers on a traditional microcontroller. So basically, you have this flat buffers file, and within TensorFlow, it can utilize this flat buffers file to generate C code based on a library that runs the model and loads the appropriate weights and coefficients. So TensorFlow Lite for microcontrollers can generate C code based on your flat buffers file that you can run really on any platform. It's very, uh, you know, doesn't have a whole lot of requirements, pretty bare bones C code library. And you can even run this on your PC too. So I may do an example of that within the class here. But that allows you to test your model um, before you even deploy it on hardware. And then the optimization libraries. So let's say that you want to TensorFlow Lite for microcontrollers provides a library, but it's not optimized for your hardware or your microprocessor. So for example, if you're using a ARM Cortex-M microprocessor, you can call CMsysNN, which is a library that has optimized functions for various processors, including ARM Cortex-M, and it will have optimized functions for the type of ARM Cortex-M processor that you're using. So for example, if you're using M0 versus M4, it'll have different optimized libraries that are the same libraries as TensorFlow Lite for microcontrollers. So you can swap libraries and you can make your machine learning model just basically run faster. A lot of these models, or a lot of these functions, the rewrite that ARM does, they're basically writing things in assembly to, you know, use the most efficient instructions possible to perform the same function. And lastly, hardware interface drivers. So, for example, if you're going to do imaging, you probably need to connect a camera, which is going to require drivers specific towards that microcontroller, that microprocessor. Same with microphones or gyros, IMUs. You're going to have specific hardware drivers for that you're going to have to integrate. So, and then just some notes that in terms of the types of microcontrollers that are used, typically they're Cortex M4 or higher, so ARM Cortex M4, M7, or some cross hybrid of, uh, you know, high-end Cortex M / A series processor. So more on the high end, even though they're microprocessors, they're really high-end microprocessors. They typically have camera or microphone interfaces, so most of the camera interfaces are only on higher end microprocessors and are fairly limited in their capabilities, but it forces it up to those higher end processors anyways, just because of the interfacing needs that are the most common use cases for machine learning. Um, Pre-processing. So, for example, if you're using a camera, you probably need to do some image signal processing, or you may need to do some image signal processing to get the image to look correct. You may need to convert it to grayscale, depending on the model you're using. Various things like that. If it's like a thermal camera, you may have to do some pre-processing. And then the last thing is that just for machine learning alone, you need lots of memory. Memory is critical in the machine learning applications. So you need quite a bit of flash to hold and store the coefficients. You're looking at normally for like MobileNet V1, you're looking at over 200K bytes of flash just for the coefficients, not including your code, and then RAM to store the layers. So you're going to need just to store each layer of the model, you're going to need, it depends on the model. If it's something like MobileNet that was actually designed for running on microprocessors and embedded hardware, then you're going to need less because those models typically have more layers, but they're not as deep. They're not as wide of layers. But if you're using like a more traditional model, that's probably going to be wider with less layers, and then you need more memory. But yeah, you're looking at, I would say, you know, MobileNet, you probably need, 100 to 200K, I believe. And then, on the higher end, if you're doing like a more traditional model, you probably need megabytes, low, like a single megabyte, couple megabytes. I believe I have a chart on that I might throw in here to illustrate that. So, in short, uh, there's limited options for microprocessors, and it forces the developers to choose higher end microprocessors, more SoC type microprocessors. And there's limited flexibility in the microprocessors for these types of use cases, microphone processing, camera processing. And so this kind of leads into where, FPGAs have a really good fit here on the low end edge machine learning processing. Also, there are some microprocessors that are coming to the market with built-in NPUs, or neural processing units. It's kind of like a graphics processing unit, helps co-process graphics data for the MCU. This is very similar, only just for machine learning. What we found, we still have a lot of customers where, machine learning is continually evolving, especially on the low end. And so a lot of the times when these uh, devices that have an NPU come out, they're they're already behind because things have evolved within TensorFlow Lite, or things have changed, and so it's very hard to, if you're going to do a dedicated chip, to keep up with the changes of software within TensorFlow Lite. So we've seen a lot of customers where they just really can't use what's available in these NPUs. But basically, it's the same flow. You just have NPU drivers to handle running the instructions in the NPU versus the MCU. And so the only gain is really more performance or lower latency in these devices, and they still focus on using a higher end microcontroller like an M4 or M7, typically. And some of them have like multiple processors in them too. So they're really more of like a SoC, which adds, cost and infrastructure and size. But if it meets your needs exactly, then it's a great device to have on the shelf. And then we have the system hardware architecture of a micro SoC FPGA, an FPGA with an embedded microprocessor. So we can take advantage of all of the same things that we talked about with the MCU and the MCU plus NPU, but with much higher flexibility. So you still have the same kind of setup, but I would say that you have much more flexibility in the NPU because it's soft. And then by I mean soft, it's in the FPGA lookup tables. And then in terms of hardware interfaces, you have way more flexibility. So first, you can utilize all of the I/O count on your device. So all of the I/O is highly flexible. Second, you can just interface to a lot more things, or different interfaces that you may not be able to do on the microprocessors. So multiple cameras, multiple CSI2 cameras, MIPI CSI2 cameras. You could add a display for displaying your content. You can add as many I2S microphones as you want. You can interface to unique and new peripherals such as MIPI I3C. So you have a ton of flexibility on the front end and back end for interfacing to peripherals, as well as very flexible block RAM memory inside the device for, basically holding front end data and pre-processing. And then you have the ability to add in pre-processing blocks, as well as in the R series of our devices, they're not traditional FPGAs in that they actually have extended memory, up to 8 megabytes of extended PS RAM, which we use to store the input and output layers. And as I mentioned earlier, the memory is really important in these use cases. So, and I'll show that on a later slide, that having 8 megabytes of PS RAM is not something that you're going to have in a typical microprocessor, but adds a lot of flexibility in the types of models that you can support. So just to summarize, FPGA provides high flexibility both in the I/O count and the IP blocks that you choose to lay down in the FPGA fabric. You can optimize your performance and your chip for what you want to do. So you're not basically paying for I/O that you're not using, and you can, utilize the I/O that you have and go into a smaller, more integrated package. And then you have a architecture. You can architect the hardware for your needs and your use case. Here are just some examples of situations that have come in with various customers that need to use the flexibility of FPGA Fabric in their machine learning projects. So one is that a lot of times for the low-end TensorFlow Lite for microprocessor type applications, they typically don't handle cases with spatial inference or bounding box conditions, because those models are fairly larger and just take a lot more compute resources. However, with the FPGA fabric, you can actually kind of do the same thing and actually, in some ways, do it better. So a lot of customers request things like being able to do inference in different regions of the video frame for like a video classification situation. And not only look at different grid points, but then also do scaling. So basically downscaling the image so that they can look into basically depth of the image and classify objects that may not classify as well just from doing a global classification over the whole image itself. So the ability to run classification at different XY coordinates and at different image depths is really valuable and something that you can definitely do with the FPGA. And you can't really do that with the microprocessor situation or other situations because you kind of need this front end hardware architecture to do it efficiently. Second one is classification of different microphones. So adding some beamforming to the front end or noise cancellation can really improve the results of audio classification, audio phrase detection. And so we see that a lot where, let's say that you have a situation where you have a microphone in the room and you have multiple microphones in the room to do beamforming and noise cancellation, and then you want to do some phrase detection or different word detection classification over time. That's something that you can do with FPGA, and you can do exactly the types of microphone interfaces you want to do. So PWM, PDM, I2S, and multiple channels of I2S as well. Third one is doing multiple different sensors and processing multiple sensors. So you can use the same hardware platform to, say, handle situations where you want to really use multiple sensors to understand what's going on. So take, for example, like a life alert type application where you've got some device on a person and you want to know if they've fallen and potentially hurt themselves. Well, you can use a camera for that, you can use a microphone for that, and you can use an IMU for that. So with the image data, you can look at the image data and classify if it looks like the person is fallen down. You can use microphone data to hear if there was a crash or a clunk, and then you can use the IMU data to know and detect if someone fell fast or slow. This is just one example of using multiple sensors and multiple models, processing multiple models to do inference on a variety of different front-end sensors. Okay, so now I'll talk about the architecture underneath the micro SoC FPGA, and specifically talk about Gowin's Go AI 2.0 hardware architecture. So if you don't know, Gowin's Go AI 2.0 is basically Gowin's machine learning platform, and it includes two parts. One is the added software development flow to go from TensorFlow Lite down to deploying on Gowin's FPGAs. And then the second part is the hardware architecture itself and the arrangement of files and firmware to deploy machine learning models on the FPGA. So you have the software element, the SDK, Go AI 2.0 SDK, and then you have the hardware element, the embedded combination of soft and hard macros within the Gowin FPGA device itself. So just kind of working left to right, as that's kind of the data flow. You have your microphone, camera, or accelerometer, or a combination of those devices kind of as your front-end sensor input. And then it's pretty common to buffer that data. So if you have a camera, you may want to buffer the frame or a section of the video frame. Same with the microphone, you may want to buffer digital audio data. And then accelerometer, same thing. You may want to gather accelerometer data over time and buffer it. Next, you have the kind of ARM Cortex M1 or M3 that is controlling the whole system. So once you have data in the buffer, you're probably going to want to push some of that data to the Go AI 2.0 accelerator, which is our NPU. And so the ARM Cortex M processor can take that initial input data and push it to the layer memory or scratch pad memory in the NPU. So the NPU utilizes the extended PS RAM of around 8 megabytes to hold the input and output layer data. And the first layer of a model is always that initial camera, microphone, or accelerometer data. I should also mention that the ARM Cortex-M memory, the ITCM and DTCM, are used for the global parameters of each layer of the model. layer control and layer count, and then also debugging this entire system. So from the Cortex-M processor, you can actually read out the individual layer data from each layer and debug that way, which is really nice. A lot of times I'll do that to during debugging, and I'll compare it to the layer output data of running the same flat buffers file on my PC, and I can make sure that I have a one-to-one match. Okay, and then so just talking about the Go AI 2.0 accelerator, or NPU, if you will, we have basically it covers 4 primary functions: depth-wise convolution, convolution, max pooling, and average pooling, as these are kind of the most compute-intensive functions within these quantized machine learning models. And then there's a controller for the PSRAM, which holds the input and output layer data. And there's also a SPI flash controller that runs in quad SPI mode to grab the weight and bias coefficients out of flash. And so layer by layer, the Go AI 2.0 accelerator ping pongs between 2 sectors of PSRAM, taking input layer data, processing it, and pushing it as output layers and to the PSRAM. And then once that output layer is computed, it can ping pong that memory by switching that output layer to now the next input layer and process the next output. So this is a high-level hardware system architecture for the platform we're going to be looking at today. Okay, and here is just explaining the memory allocation one more time. So the ARM Cortex-M memory, the ITCM and DTCM, it holds first any control that's needed for the system, but then in terms of the model itself, holds all of the parameters and the number of layers, as well as any functions that the NPU doesn't run for the model. So basically, layer by layer information is performed by the MCU, and then the NPU processes each layer, and the PSRAM basically supports holding the input and output layers. And then the very first layer of input data is initially stored in, there's 2 options, but mainly it's stored in a separate buffer and then is transported into the MPU. So that first layer, you can think of it being kind of in the input data buffer, but can also be, then it's also transferred to the PSRAM through the Cortex-M processor. This is the slide I was alluding to earlier about the memory sizes to process various quantized models. So if you look at bullet number 3, you can see this is for various models, the largest input layer plus largest output layer, to get an idea of how much, in our case, PSRAM you would need. And then I only have one example for the flash required, but this is the flash for MobileNet V1 to know how much flash you would need to store the coefficients. The int8 version, quantizing it to int8, which is more common, and I believe the unsigned int8 has been removed from TensorFlow now. It's a little bit larger because there's an extra multiplier coefficient per output value. So it's a little bit larger, but I think it's still in the 200K region, 200 to 300K. Okay, we've already kind of discussed it verbally, but now we're going to just discuss the design flow that we're going to do today to go from a model, training it, all the way down to deploying it on the FPGA. So first, we're going to grab a data set, and in this case, we're going to do person detection. So we're going to grab the Cocoa data set, and we're going to parse that for person, no person. And then we're going to grab a model. In this case, we're going to use MobileNet v1. And then we're going to train that model to detect person or no person. We're going to do that in TensorFlow and Keras. Then we're going to run some additional function calls to quantize and optimize the model into a TF-Lite flat buffers file. So that's the first part. That's kind of all done in the TensorFlow Keras environment. And for this case, we're going to use Colab for that. And then the second part is actually deploying it on the hardware. And I may discuss some test capabilities as well, but of how you would run this like on your PC and how you would compare. But the deployment for the FPGA is really done in pretty much one setup. You just basically set up a batch file for the paths of all the software that we discussed earlier. The Gowin EDA tool, Kyle, and I think there's a path for the TF-Lite file. And then you run that batch file, and it goes through and generates the C code and microcontroller firmware. It generates the FPGA bitstream or FPGA firmware that holds the hardware architecture for, in this case, image sensor input to the NPU and MCU architecture with the front end buffer. And then it'll also strip the weight and bias coefficients that will get stored in SpyFlash, and then it will load all these to the board actually. So basically, once you set up the batch file, you just double click every time, and it'll just load up your board with the whole design. That's all you have to do. So really, in this case, we're going to go through this, and you'll see that for just doing, kind of the basic, any sort of image sensor solution, you can just use this board and you don't have to program any FPGA, Verilog, or VHDL, and you don't have to even program any C code. It will go through and do everything for you. So let's get started with that. Okay, so now we're going to look at our Colab script, which is using TensorFlow and Keras to train a model for person or no person using the Cocoa dataset and MobileNet v1 model. And then we'll use some of the TensorFlow Lite functions to generate the flat buffers TF-Lite file. And yeah, so let's do that. All right, so here is our model, our person detection model. And so the first thing that we're going to do is we're going to just set things up. So here we're just importing everything that we need to use. Okay. And then we're going to download the data set, our person detection data set, which is originally based off Cocoa. We've done a more optimized data set for ourselves, but it's originally based on Cocoa. So that's extracting. Okay. All right. And then we're going to configure default. So image size. So the input to our MobileNet V1 model is 96 by 96 and 96 by 96 pixels. And we're just setting the database directory. So depending on how familiar you are with Colab, you can click on here, and this has all your directories in the cloud. And then some network parameters. So yeah, just some network parameters. So we'll go ahead and run this. Okay, now we'll load the data set. So, and we're normalizing the data set. So this is between -1 and 1 for the input layer, the image. We're also converting to grayscale, just FYI. Okay, this is just to double check things, just to show the first 25 images of the data set. So just to verify that everything worked on that normalization and the sizing to 96 by 96. And this also shows the associated value for the classification. So 1 means there's a person in the image, 0 means there's not. And that's in our data set that we've already created. Okay, now we're going to build the model. So you can see here that we basically have our convolution, depth-wise convolution, we're just using average pooling in this case. And then we have the model with all of the convolutions. And yeah, this is a reduced size model here. So this isn't the full MobileNet V1 model. It's modified to only do a fewer number of layers. So then we're going to run that. That sets up the model. And now we're going to train. So this would normally take a while, but since we did that reduced model, it won't quite take as long. But for the sake of time, I'm going to let this run, and then I'll stop the video, and once it's done, then we'll come back and do the rest. Okay. So basically, it just goes through and does 500 epochs of training on this model. So I'll come back when it's done. Okay, now that we've trained the model here, we can move on and run the rest of this. So this just shows the training history and the improvement over the training. And then lastly, we're going to create the TF-Lite file. So I'm going to delete this because I actually just ran through it. Make sure everything worked. So we'll hit run here. So this is going to generate the flat buffers file for int8 input and output. And then all the intermediate layers will be 8-bit integer as well. So it's running. This is going to throw an error because I don't think I have this set up to download the files directly. So, but it will generate the TF-Lite file, and we can just download it manually. Yeah, so let's go ahead and, where is it? Oh, there it was. Shoot. These are home. No. Which folder is it? Here we go. Okay. So we'll just download TF-like file. Cool. Okay, so now we're ready for hardware deployment, and I'm going to first talk about the development boards that we have for you to prototype the machine learning classification solutions and inference solutions that we have available as a starting point. So the first board is our smallest board, and this is based on the GW1NSR4P device. And there's actually two development boards. There's a version 1 and a version 2. The version 2 is about half the size and has the IMU on it, whereas the first version is a little bit bigger, has an HDMI output, and doesn't have the IMU. So this device has about 4.5K lookup tables. It has a embedded hardened Cortex M3 microprocessor. It has 8 megabytes of additional PS RAM. This is in addition to the I think it's about 180K bits of block RAM in the FPGA. So this is extended memory. And it's in a 6mm by 6mm QFN48. There's other packages available, but that's just what's on this board. The PCB has a camera connector for a OmniVision 2640 camera. This is also compatible with other OmniVision cameras, other similar parallel interface cameras, as well as the Himax HB01 camera, which is pretty popular for machine learning type applications, very low power camera. Let's see, what else? The chip itself is also able to do things like MIPI CSI2 and source synchronous serial camera interfaces. It just so happens that this particular demo uses a parallel camera. Let's see. There's two I2S microphones, I believe. One or two? I think one. Sorry. One I2S microphone. This is the SPH0645 I2S microphone, but more could be connected to the device. You can do basically as many I2S interfaces as you want. And there's an IMU on the version 2 board also. And then there's externally on the PCB, there's 64 megabits of SPI flash. This is used to hold the coefficient data. And an HDMI TX port. Unfortunately, the machine learning design takes up the majority of the device, and there's not enough room on this particular device to have HDMI output. But this can be used for things outside of machine learning, or potentially in the future, if we do a more optimized version of the MPU, we might have room to utilize the HDMI output on this board. The HDMI TX, I should say, is only available on the version 1 board. The version 2 is too large, or it's too small a board to have such a interface on. And also the I/O is needed. The next board we have is the Gowin AI GW2AR18P development board. This board has significantly more FPGA lookup tables, 21K lookup tables in total. It's in a 10mm by 10mm QFN package. Other packages are available, but this is the one on this particular development board. Same situation with the cameras. OmniVision 2640 comes with the board, but there's other options as well that are compatible with the same connector. This board has HDMI RX and TX, and there's enough room to have that, and we use that in a lot of the demos. So this is kind of nice to have HDMI RX and TX because you can use an HDMI input stream during your development for video inference applications. And then also you can output the video with, we have a text overlay. We have a text overlay, bounding box type capabilities within the design, and you can add those to your output, your HDMI output. There's internally 4 megabytes of PS RAM. This is actually wrong. There's 8 megabytes of PS RAM, but in this case, it's distributed over 2 interfaces, so you get twice as much bandwidth on this one. They're 4 megabyte blocks each, and then there's 2 of them. 32 to 64 megabits of SPI flash externally, which is used for the bit stream loading. This device is a volatile device. It doesn't have built-in flash, so you can load the design from external SPI flash, and then you can also utilize the coefficients by reading them from SPI flash. There's LEDs on this board, as well as the other boards, and a USB programmer is built into this board, as well as the other boards. This particular demo for Go AI and machine learning uses a soft Cortex M1 processor, and the next board will as well. The only one that has the hardened Cortex M3 processor is in the smallest device, the GW1NSR4. Lastly, we have the Go AI GW2A55 development board. This board uses a 55K lookup table FPGA. This device does not have the embedded PS RAM and instead uses an external Cypress HyperRAM part. Um, this is just to show another option. So the reason why is this is a bigger FPGA. You may want to use external memory like DDR or external HyperRAM, multiple HyperRAMs. And so it's just showing a different option. And this is using a larger package. There's really no reason for it. It's just a common package for the 55K. There's much smaller packages as well. I believe something in the QFN is also available. There's same camera is on this board. Again, it's compatible with other cameras. The I2S microphones, the IMU is on this board. HDMI RX and TX, and all right, now that we've looked up the boards and we've chosen a board, now we need to set up the Go AI 2.0 SDK repository. So the first step is to pull the GitHub repository, which is github.com/goinsemi/goai.git. After that, you're going to navigate to the bin folder and the goai_run.batch file for the particular board that you're using and the particular demo that you want to run. So in this case, we're doing person detection, and I'm going to use the GW1NSR4 board. And then you're going to open that batch file and edit the paths located right at the first set of script lines. So there's 3 paths. The first one is the directory to your TF-Lite file. The second one is the path to Gowin programmer. And it turns out that it's built into the SDK. So you actually don't need, I think I mentioned earlier that you needed Gowin EDA tool. You don't actually. The programmer, you don't need a licensor, and you don't need the full Gowin EDA. The firmware for the FPGA bitstream is static for the camera, microphone, and IMU designs. It's just a black box architecture for each sensor input. And then the last path is to Kyle. So, okay, now that we've updated the batch file, we'll need to run it. Okay, so now I have updated my paths in the Go AI batch file, and I have added the TF-Lite file to my data directory under TF model. And so now I just need to run the batch file. Pretty simple. So here we go. I've got the board plugged in. I am turning the board on. I'm going to use the GW1NSR4 Go AI board, and I run the batch file. So first it's going to generate the Cortex M3 C code. Then it's going to generate the FPGA firmware for the particular design, in this case, camera input. And it's going to then load that to the board. First it also extracts the TF-Lite model file and then generates the C code. And the necessary extracts the weight and bias coefficients. So first it's loading this external SPI flash. That's with the weights and bias. On this board, then it will program the FPGA with internal flash. On the other boards, it will be external flash, but this one has built-in flash memory. And then it will load the Cortex M3 with the necessary C code. And that's it. So to recap what we've just done, we downloaded the Go AI GitHub repository and pulled the repository. We installed the software dependencies, Python, Kyle, and Gowin Programmer. No need for Gowin EDA. We've updated the paths in the batch file, and then we executed the batch file script, which parses the flat buffers file for model information needed to generate the C code for the Cortex M processor, and then extracts the coefficients, which are loaded into external SPI flash. The C code is then generated and compiled, and the FPGA firmware is already pre-synthesized, so it just loads the FPGA firmware for the microphone, camera, or gyro demo that we're running. And then we deploy the model onto the board by loading the external SPI flash with coefficients, loading the Cortex M microprocessor with the C code, and then loading the FPGA bitstream or firmware with the hardware design. So now I want to show a series of videos starting with the person detection demo, and then I'll show, since that's the one we loaded to the board, so you can get an idea of what the demo looks like on the GW1NSR4 small board, as well as the 55K larger board with the HDMI output. And I will say that the person detection demo is quite a bit better than when it was in this video, particularly the 4K, because we use a fisheye lens camera. I think in the video I'm just using a standard camera lens rather than the fisheye, so it's hard to line up, and there's no HDMI output on it. So it's a lot better now. It works very well now. 55K is a little easier because you have the video output. But also it's improved because of the fisheye lens and some other model improvements. So yeah, we'll show that one, and then we'll show some digit detection. We'll show I believe we have a car detection, and then we'll do audio phrase, and I'm not sure if we have anything on gesture, but these are, I'll play the videos that I have. Gowin is pleased to present a human's presence detection demo at the edge using Go AI 2.0. Model development is performed in TensorFlow, quantization in TensorFlow Lite, and Go AI 2.0 SDK compiles accelerator and MCU firmware. With the Go AI 2.0 development boards, you can provide a variety of sensory inputs and perform object classifications using Go AI 2.0. In this demonstration, we'll show object classification of cars and people using an HDMI input source. The benefit of this is that you can provide any number of video streams from a PC very easily during the development stage of your machine learning solution. HDMI input is available on the GW2A series Go AI 2.0 development boards, and is not included on the GW1NSR4 development board due to lower pin count. However, the object classification for cars and people is provided with a camera input for the GW1NSR4 and is just as able to perform the same classification demo as the larger devices. So for development purposes, we provide these larger boards with HDMI input for better debugging. This video shows Gowin's Go AI 2.0 machine learning and inference solution and coprocessor for digit classification. Go AI 2.0 development boards can be used with a camera input. The camera can be pointed at digits of 0 through 9 that are handwritten or machine typed. The camera image runs into an image buffer, which can then be fetched from the ARM Cortex-M processor and loaded into the Go AI 2.0 machine learning coprocessor. The machine learning coprocessor can be loaded with a model to detect these digits, and the inference output, in this case, has 10 classification outputs for each digit. This is then ran to 10 GPIOs, which can drive 10 different LEDs. It also runs to a text overlay to provide the classified digit name overlaid on the HDMI output. Here, for example, you can see that the camera in the diagram is pointed to 3, and the text overlay says 3 as a result of detecting that digit. All processing in this demo is done at the edge in the embedded device itself. For more information, you can email us at info@gowinsemi.com or go to our website, www.gowinsemi.com. Detecting multiple digits can be performed with Go AI 2.0 using a small digit classification model and a region of interest controller. The region of interest controller resides in the FPGA and receives the X and Y coordinates from the Cortex-M microcontroller embedded in the Gowin device. Classification of objects using a region of interest adjustment allows for less resource-intensive models to be used over larger models with spatial inference capabilities, reducing solution cost, power, and form factor. The same design can be used for classification of different types of objects within a video or camera stream. Here we have a clock with its hands pointed at various locations being inferred by the Go AI 2.0 NPU. For unique classification scenarios, a custom image database must be created related to the types of images that are to be classified and the environment to which the objects will reside in. Gowin Semiconductor's Go AI Design Services team supports the creation of custom databases and models which are deployable on the Go AI 2.0 platform and NPU.
Yes, yes, no, 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 yes, yes, no, no, yes, yes, no, no, yes, yes, no, no, yes, 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 no, 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 yes, 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 no, no.
Okay, so that concludes what I had planned for this class today. I hope that you got an idea of the process that is required to target small embedded devices with machine learning capabilities, whether they be FPGAs, microcontrollers, or a combination of them. And just some resources. So Gowin is continually making new example designs and it continually updating the Go AI 2.0 SDK. And so you can actually just keep an eye out for new videos on goinsemi.com. That's a good way to kind of see different applications and examples as they develop. Also, a good book if you're completely new to TinyML or TensorFlow Lite for microcontrollers is the TinyML book. It's, it goes through, we leverage a lot of those examples, or we did starting out, and we just took those and then built NPU around them. But it's a basic microcontroller. Has basic microcontroller examples that all can be transported over to Go AI since we support TensorFlow Lite for microcontrollers. So anything in that book is completely applicable to Go AI 2.0 and beyond. We've definitely gone beyond that book, but it was a good starting point. Development boards are available through our distributors, so you can go to our distributor page on goinsemi.com to find out who would be the best choice for obtaining development boards. And then if you have any questions, thoughts, comments, of course, I'm happy to answer your questions here as we have plenty of remaining time. But also, if you think of something later, you can, of course, go through the embedded world material or platform, but also you can reach out to us through our inquiries page, email us at info@goinsemi.com, or this is my direct email, grant@goinsemi.com. So that's it. Thank you very much, and I hope that this class was beneficial. Thank you very much.